You know, it's funny, the more you sort of look around and think about things, the more patterns you kind of start to see. Like everywhere you look, there's some kind of order, right?
Yeah.
Whether it's, I don't know, the dynamics in your family or, the structure of some elegant math equation, there's this sense that things are kind of connected in a predictable way.
Yeah, totally. Like there's this underlying order to the universe almost. And it's like we're trying to, I don't know, decode it or
Yep,
something.
exactly, exactly. And there's this great quote by Berthelot. He said, mathematics is the indispensable instrument of all physical research, which I think it kind of sets the stage for what we're going to be talking about today, because at the heart of it, math is all about finding and understanding these patterns, these connections. And one of the most fundamental ideas in math that helps us do that is this concept of relations.
Right. And relations are basically like just a way of formalizing how things are connected. Like simple comparisons we make all the time. Saying something like, my height is greater than yours, or, this street runs parallel to that one. Those are examples of relations. We're linking two things together
Yeah.
based on some kind of comparison or rule.
Okay, so that makes sense. So, like, if we're comparing heights, those two things, those two objects are heights, and the relation is greater than.
Exactly. And in math, we like to be very precise about how we define these relations. We usually start with two sets of objects, anything really, and then we look at pairs of objects, one from each set. And we define a rule or a condition that tells us whether those two objects are related or not.
Got it. So, the mission then for this deep dive is to really unpack this idea of relations. How do we take pairs of objects from two different sets, figure out how they're related, and then ultimately, how does that lead us to the super important concept of functions, which I know we'll get to?
Absolutely. Functions are kind of like the superstars of relations. They're super useful, and we use them everywhere in math. But yeah, to get there, we got to start with something called the Cartesian product of sets, which sounds kind of intimidating, but it's actually a really simple idea.
Okay, Cartesian product. Lay it on me.
All right, so imagine you have like two baskets of fruit, right?
Yeah.
One basket has apples and oranges, and the other one has bananas and pears. The Cartesian product is just a way of listing out every possible combination of one fruit from the first basket and one fruit from the second basket.
So, like apple banana, apple pear, orange banana, orange pear.
You got it. That's the Cartesian product of those two sets of fruit. It's just all the possible pairs you can make.
Okay, I'm starting to see how this relates to, like, the color and object example we have in our source. So we have set A, which is colors, red and blue, and set B, which is objects, bag, coat, shirt. And we're going to represent those with the letters B, C, and C just to keep things tidy.
Right, exactly. So if we take the Cartesian product of those two sets, we get all the possible color object pairs. So we'd have red B for red bag, red C for red coat, red S for red shirt, then blue B, blue C, and blue S.
And that's it, 6 distinct ordered pairs. Our source actually has a helpful little diagram, it's figure 2.1, that visually shows how this pairing works. It's like a little grid, kind of neat.
Yeah, those visual representations are super helpful. But the main point is we've now created all the possible combinations of one element from the first set and one element from the second set. That's the essence of the Cartesian product.
Okay, so we've got this intuitive idea of pairing things up, but how do we express that formally, like in a proper mathematical definition?
All right, so if we have two sets, let's call them P and Q, the Cartesian product, which we write as PAQ, that P with a little x for times. And then Q, it's the set of all possible ordered pairs, written like this. PQ, where P is an element from set P and Q is an element from set Q. Remember, these are ordered pairs, meaning the order matters. The pair PQ is not the same as the pair QP.
Right, the order matters. That makes sense. Like in that fruit example,
Hmm.
apple banana is definitely not the same as banana apple.
Exactly. And one other thing, just a little detail, but important. If either P or Q is the empty set, meaning it has no elements, then their Cartesian product, PAQ, is also empty. You can't make any pairs if one of the sets has nothing in it.
Makes sense. All right, so I think I've got the gist of the Cartesian product now, but I always find it helpful to see a few more concrete examples to really solidify the concept.
Yeah, for sure. Example 2 in our source is a good one. Imagine we have a set A that represents some states in India, DL for Delhi, MP for Madhya Pradesh, and KA for Karnataka. And then we have set B, which is a set of numerical codes, 01, 02, and 03. Now, let's say these states want to create license plate codes that start with one of these letters and are followed by one of those numbers.
So, like, how many different possible license plate codes could they make?
Exactly. And the answer lies in the Cartesian product. If If we take AAB, we get all the possible combinations. We have DLO1, DLO2, DLO3, then MPO1, MPO2, MPO3, and finally KAAO2, KAO3. 9 possible codes in total.
And again, that's all visually laid out in figure 2.2 in our source. It's like a little table, which really helps to see it clearly. But the key point here is that the order really matters. DL01 is a totally different license plate than O1DL.
Right, exactly. I mean, imagine the chaos if those got mixed up.
Okay, so one last example just to hammer this home. Let's say we have set A, which contains A1 and A2, and set B, which has B1, B2, B3, and B4. So what's the Cartesian product of those two sets?
Well, if you pair up every element from A with every element from B, you get a total of 8 ordered pairs. And a cool thing is, if these elements were, say, numbers, we could think of those ordered pairs as representing points on a graph. So the pair A1, B2 would represent a different point than B2, A1. Again, order matters.
Right, and we can see that in figure 2.3 in our source. It shows how these ordered pairs can map onto a plane. So we've really covered how to create these pairings, these Cartesian products. But there are a few important things to remember about them, right?
Totally. So first off, for two ordered pairs, let's say A, B, and X, Y, to be considered equal, both their components have to match up exactly. A has to be the same as X, and B has to be the same as Y.
Makes sense. What about the total number of elements in a Cartesian product? Is there a way to figure that out quickly?
Yeah, it's pretty straightforward. If you have a set A with P elements and a set B with Q elements, their Cartesian product, AAB, will have P times Q elements. So if you have like 3 colors and 4 objects, you'll have 12 possible color object combinations.
Right, okay. What about, what if the sets have an infinite number of elements? What happens then?
That's where things get really interesting. If either set A or set B is infinite and not empty, meaning it goes on forever, then their Cartesian product is also infinite. You basically have endless possibilities.
Mind-blowing. And just as a quick aside, we've been focusing on ordered pairs, but you can actually have ordered triplets or even longer sequences. If you take the Cartesian product of a set A with itself 3 times, like A, you get ordered triplets written like this, ABC.
Right, and that's how we start to think about higher dimensions in math. Okay, I think we've talked enough about the abstract stuff. Let's dive into some examples.
Yeah, let's get our hands dirty with some problems. So example 1 gives us this equation, x plus 1, y2 equals 3, 1. And it asks us to find the values of x and y. How do we even approach that?
We remember how we said for two ordered pairs to be equal, their corresponding components got to be equal, right?
Right.
So we can basically set up two separate equations. X plus 1 has to be equal to 3, and y2 has to be equal to 1.
Oh, I see. So it's just a matter of solving those two little equations.
Exactly. And those are pretty easy to solve, right? X plus 1 equals 3 gives us x plus 2, and y2, 1 gives us y plus 3. Done.
Nice. So example 2, it gives us two sets. P, which is A, B, C, and Q, which just has R in it. And we're supposed to find the Cartesian products PAQ and QPAP and see if they're the same.
Right, so let's do it systematically. PAQ means we pair each element from P with the element R from Q. So we get A, R, B, R, and CR. For QAP, we do the opposite, pairing R with each element from P. So we get RA, RB, and RC.
And are those two sets equal?
Well, let's compare them. We have AR in the first set, but that's not the same as ARA in the second set, right? The order matters.
You're right. So even though both sets have the same 3 pairs, just in a different order, they're not considered equal because the ordered pairs themselves are different.
Exactly. The order within the pairs makes all the difference. Okay, example 3. This one's a bit more involved. We've got 3 sets. A, which is 1, 2, 3, B, which is 3, 4, and C, which is 4, 5, 6. And we're asked to look at how Cartesian products play with other set operations, like intersection and union.
Okay, set operations. I vaguely remember those.
Right, so intersection means you take the elements that are common to both sets. Union means you combine all the elements from both sets without duplicates. So first we have A, G, C.
So we got to find the intersection of B and C first.
Yep. What do B and C have in common?
Just the number 4.
Right, so BC is just 4. Now we take A4, which means pairing each element from A with 4. That gives us 1, 4, 2, 4, and 3, 4.
Okay, I'm following now. What about AAB, AAC? Do we have to calculate those Cartesian products separately?
We do. So AAB, if you pair up all the elements, you get 1, 3, 1, 4, 2, 3, 2, 4, 3, 3, and 3, 4.
Okay, that's 6 pairs. And what about AAC?
But for AC, you get 1, 4, 1, 5, 1, 6, 2, 4, 2, 6, 3, 4, 3, 5, and 3, 6. 9 pairs this time.
Okay, so now the intersection of those two sets. We need the pairs that are in both AAB and AAC.
Exactly. And if you look closely, the pairs that appear in both sets are 1, 4, 2, 4, and 3, 4.
Huh, interesting. That's the same result we got for AABC. Is that a coincidence?
Not at all. This illustrates a cool property of how Cartesian products interact with intersections. You can do AAC, BC, or you can do AAC, B, AC, and you get the same result.
Nice. So does the same thing happen with unions?
Let's find out. AABEC
Yeah.
first. The union of B and C is 3, 4, 5, 6 because we combine all the elements.
Right, and then we take AA3, 4, 5, 6, which will give us a bunch of pairs.
It'll be 12 pairs, to be exact. Now, for AAB, AAC, we take the union of those two Cartesian products we calculated earlier.
And that means we just list out all the pairs without repeating any.
Yep. And you'll find that the result is the same set of 12 ordered pairs that you got from AAB. So, again, the distributive property holds. You can do AABC or you can do AABB, then you'll get the same thing.
Cool. So these Cartesian products, they play nicely with other set operations. What's next?
Example 4 takes a set P, which is 1, 2, and asks us to calculate PAP.
So we're taking the Cartesian product of a set with itself 3 times.
Exactly. This gives us ordered triplets. We're basically listing all the possible ways to choose one element from P, then another, then another.
Okay, so let's see. We could have 1, 1, 1, 1, 1, 2, 1, 2, 1, 1, 2, 2, 2, 1, 2, 1, 2, 1, 2, 2, 1, and 2, 2, 2. 8 possible triplets in total.
Right. And as we mentioned earlier, this idea extends to even more dimensions. You can take the Cartesian product of a set with itself as many times as you want, and you'll get ordered sequences of that length.
Okay, starting to get a bit abstract now, but I have a feeling example 5 is going to bring it back down to earth a bit.
You got it.
Yeah.
So example 5 talks about the set of all real numbers, which we usually denote with the letter R. Now think about RAR, the Cartesian product of R with itself. What do you think that represents?
Well, we're pairing up real numbers with real numbers. Does it have something to do with, like, coordinates on a graph?
Exactly. Every point on a two-dimensional plane can be represented by an ordered pair of real numbers, its coordinates.
Yeah.
So RAR is basically the set of coordinates for all the points in a two-dimensional space.
Wow, that's cool. So, like, every single point on a graph can be represented by an element in this Cartesian product, RAR. And what about RA cars AR?
That extends the idea to 3 dimensions. AR represents the set of coordinates for all the points in 3-dimensional space. It's like taking a regular XY graph and adding a third axis, the Z-axis.
Okay, that's starting to wrap my head around how we use Cartesian products to describe spaces, like the space we live in.
Exactly. It's a foundational concept in geometry and all sorts of other areas of math. All right, last one, example 6. This time we're given the Cartesian product AAB, which is a set of ordered pairs, PQ, PR, MQ, and MR.
And we need to figure out what the original sets A and B were.
Exactly. It's like working backwards. So remember, set A is a set of all the first elements in those ordered pairs.
So looking at the pairs, the first elements are P and M,
Right, so AAPM. And similarly, set B is the set of all the second elements.
which are Q and R. So B, E, Q, R.
Perfect. Got it.
Mm.
So even if an element appears multiple times in the Cartesian product, like P does, we only include it once in the set.
Got it. Okay, so we've covered a lot of ground here with Cartesian products. We've seen how to create them, how to calculate them, how they interact with other set operations, and even how they relate to the spaces we live in.
Exactly. And all of this forms the basis for understanding this next big idea, relations. Remember those simple comparisons we talked about earlier, like greater than or parallel to?
Mhm.
Those are examples of relations.
Right, so how do we formally define a relation in the language of math?
Well, a relation from set A to set B is basically any subset of the Cartesian product AAB. It's a way of picking out certain pairs from all the possible pairs based on some specific rule or condition.
Okay, I think example 7 in our source might help to make this clearer. We have set P, which is A, B, C, and set Q, which is a bunch of names. Ali, Banu, Binoy, Chandra, and Divya.
Right, so if we take the Cartesian product of P and Q, we get 15 possible ordered pairs. But then a relation is defined as a subset of this Cartesian product based on the rule. X is the first letter of the name Y.
So we're only interested in pairs where the first element, which is a letter from set P, is the first letter of the name in set Q.
Exactly. So the relation R in this case would be A, Ali, B, Banu, B, Binoy, C, Chandra. Notice that C from set P is only related to Chandra in set Q, even though there are other names in Q that start with C.
Right. And B is related to both Banu and Binoy because both those names start with B. And there's a cool arrow diagram in figure 2.4 that shows these connections visually. It really helps to see it that way.
Visualizations are definitely helpful. Okay, so that leads us to definition 2. A relation R from a non-empty set A to a non-empty set B is any subset of AAB. This subset comes about by specifying a relationship between the first and second elements of the ordered pairs. And the second element in a pair is called the image of the first element under that relation.
Okay, so a relation is just a bunch of ordered pairs, but those pairs are chosen according to some rule. And we call the second element the image of the first element.
Exactly. And this relationship can be defined in a couple of ways, right? Either by listing out all the pairs that satisfy the rule, which we call the roster method, or by stating the rule itself using mathematical symbols, which is called the set builder method.
Okay, makes sense. So now we come to the terms domain and range, right? I always get those mixed up.
Well, the domain of a relation is simply the set of all the first elements, all the inputs, basically, that appear in those ordered pairs that make up the relation. And the range is the set of all the second elements, all the images, the outputs.
Okay, domain is inputs, range is outputs. Got it. But there's also something called the codomain, right?
You got it. The codomain is the entire set that the second elements could potentially belong to. So the range is always a subset of the codomain, or sometimes they can be the same.
Okay, that clears things up a bit. So we have these three ways of representing relations. Algebraically, either by listing all the pairs or writing a rule, and visually using arrow diagrams.
Exactly. Example 7 shows us how we can define a relation algebraically. We have the set A, which is 1, 2, 3, 4, 5, 6, and a relation R defined by the rule y equals x plus 1 tag. This is the set builder way of defining it.
So the rule is take an element from set A, add 1 to it, and that gives you its image.
Precisely. So the relation R, if we list out all the pairs, would be 1, 2, 2, 3, 4, 4, 5, 6. Figure 2.5 in the source shows this relation as an arrow diagram, which really helps to visualize it.
Okay, I'm seeing how those representations connect. What's the domain and range of this relation?
The domain is all the first elements, 1, 2, 3, 4, 5. Notice that 6 is not in the domain, because there's no element in A that you can add 1 to and get 6. The range is all the second elements, 2, 3, 4, 5, 6. And the codomain in this case is the same as the original set A, which is 1, 2, 3, 4, 5, 6.
Got it. What about example 8? That one shows us a relation visually, right?
Right. Figure 2.6 shows a relation between two sets. Let's call them P and Q. Looking at the arrows, we can figure out the rule. X is the square of Y.
So each arrow points from a number in Q to its square in P.
Exactly. Now, to write this relation algebraically, using set builder notation, we would say Rxyx is the square of Y, XEPYQ. It just means that for every pair, x, y in the relation, x must be the square of y.
And the roster form would just list out all those pairs, right?
Yeah.
So R, 9, 3, 9, negative 3, 4, 2, 4, negative 2, 25, 25, 9, 5.
Perfect. And the domain of this relation is 4, 9, 25, all the x values. And the range is negative 2, 2, negative 3, negative 5, 5, all the y values. Notice that 1 insult q isn't related to anything in P because 1 squared is still 1, which is not in P.
Right. So some elements might not be used in a relation. What about the total number of possible relations between two sets? Is there a way to calculate that?
There is. It's actually pretty amazing. If a set A has P elements and set B has Q elements, the total number of possible relations from A to B is 2 raised to the power of P times Q.
Wow, this seems like a lot.
It can be, especially when the sets are large. Think about it. Each subset of the Cartesian product, AAB, represents a unique possible relation. And there are a ton of subsets when you have a lot of elements.
Okay, my brain is starting to hurt a little, but example 9 gives us a concrete example of this, right?
Now, so we have A, 1, 2, and B, 3, 4. Both sets have 2 elements. So the number of elements in AAB is 2 times 2, which is 4. Therefore, the total number of relations from A to B is 2 to the power of 4, which equals 16. 16 different ways to relate those two tiny sets.
Okay, I'm going to have to take your word for it on that one. Just one more quick clarification.
Sure.
What about relations where the sets are the same, like a relation from A to A?
Oh, yeah, good point. We simply call those relations on A. It's just a special case where the inputs and outputs come from the same set.
All right, so we've really built up a solid understanding of sets, Cartesian products, and relations, but now we got to talk about the main event functions. What makes them so special?
All right, so a function, let's call it f, from a set A to a set B, is a special kind of relation. The key difference is that every single element in A has one, and only one, image in B. Every input has exactly one output.
Okay, that one and only one part seems really important.
It is. It means two things. First, The domain of the function has to be the entire set A. Every element in A has to have a corresponding output in B. No input can be left out. And second, no two different pairs in the function can have the same first element. You can't have one input giving you two different outputs. It's like a very reliable machine. You put something in, you always get the same thing out.
So it's like a special, more restricted kind of relation. Is there a special notation for functions?
There is. We write f, AE, to indicate that f is a function from A to B. And if AB is a pair in the function, meaning A from A is related to B from B by the function f, we write it as FAB.
Okay, so FAB basically means that when you put A into the function f, you get B out.
Exactly. And we call B the image of A of the function f, and A is called the preimage of B.
Got it. Now, I'm curious to see if any of the relations we looked at earlier qualify as functions.
E2. Let's go back and see. So example 7, where we had the relation r yx plus 1 from A to A, where A was 1, 2, 3, 4, 5, 6. Do you think that's a function?
Well, the rule was y equals x plus 1. So every element in A does have an image except for 6, because 6 plus 1 is 7, which is not in A.
Exactly. So because 6 doesn't have an image within A, this relation is not a function. It violates that first condition we talked about,
Yeah.
that every element in the domain has to have an output.
Okay, I see. What about example 8, where we had that visual relation with the squares?
Remember, the relation was r of 5, 9, 3, 9 is 3, 4, 2, 4, 9 is 2, 25, 5, 25 minus 5. Is that a function?
Well, 9 is related to both 3 and line to 3 because they both square to 9. So that violates the second condition for a function, that one input can't have two different outputs.
You got it. So that relation is not a function either.
Okay, so example 7 and 8, they're relations but not functions.
Exactly. And example 9, while it didn't show a specific relation, it highlighted that out of all the possible relations between two sets, only some of them will actually be functions.
Right, they have to follow those two strict rules. So functions are like the elite club of relations.
You could say that. They're the ones that give us this incredible precision and predictability.
So to wrap up, we started with this idea of Cartesian products, which is just a way of systematically pairing up elements from different sets.
Then we moved on to relations, which are subsets of those Cartesian products, chosen according to some rule. And finally, we zoomed in on functions, which are those special relations where each input has one and only one unique output.
And it's that simple constraint that makes functions so incredibly powerful. It allows us to describe all sorts of phenomena in the world, from the motion of planets to the behavior of algorithms.
And that's precisely why functions are so important. They provide a rigorous framework for understanding and analyzing all sorts of relationships.
It's really quite amazing, isn't it, when you start to think about it? This idea of a unique output for every input is everywhere. It's in the way computers work, in the laws of physics, even in the way we make decisions.
It's a fundamental principle that underlies so much of how we understand the world.
So for all our listeners out there, here's something to ponder. As you go about your day, try to notice all the instances where this principle is at play. How might understanding the concept of a function give you a new way of looking at those things? It's a question worth thinking about.